We will now look at the other assemble method based on decision trees, boosting. We will start with a generic presentation of boosting, then we will study the algorithm in detail, which we will particularize to the case of decision trees. Boosting consists in aggregating individual predictors that are weak, i.e. not very predictive, in a sequential manner in order to obtain an aggregated predictor with better performance. The predictor that results from boosting is nothing more than a weighted average of the individual predictors, where each of the individual predictors has been trained on a modified dataset compared to the original dataset. To apply a boosting method, we need a dataset Dn, a training procedure, and a loss. In the following, we will choose decision trees as a learning procedure. But boosting is a more generic method which can be applied to other predictors, for example, linear predictors. Here is a generic presentation of boosting in a scheme. From the original dataset Dn, we will, at iteration t equals 0, apply the previously chosen learning procedure, for example, decision trees. In this way, we obtain a predictor f0, which is our aggregated predictor at iteration 0. In the next iteration, we consider a modified dataset d tilde 1n, in which the original labels of the dataset are replaced by the residuals associated with the predictor f0, the aggregated predictor obtained in the previous iteration. Residuals do not have a general definition. For example, in regression with quadratic loss, the residual is the difference between the true label of the data and its prediction. We then apply the learning procedure on this modified dataset in order to predict the residuals of the previous iteration. This step produces an individual predictor noted h1, and we then seek to combine this individual predictor with the aggregated predictor of the previous iteration in a linear fashion. Thus, we look for the best coefficient alpha1 such that the previous aggregated predictor f0, to which we add alpha1 h1, has the lowest error. Thus, we see here that this procedure is iterative. We constructed a predictor h1 from the residuals, i.e. errors, of the predictor f0 to obtain a combination f0 plus alpha1 h1 that has a smaller error. The predictor f0 plus alpha1 h1 is thus the aggregated predictor in step 1. We then repeat the same procedure considering the residuals of this aggregated predictor. Specifically, in iteration 2, we construct a modified dataset with the residuals of the aggregated predictor from iteration 1 as labels. Applying the learning procedure, we construct a tree, h2, which is then combined with the aggregated predictor from step 1 to obtain a new aggregated predictor, f0 plus alpha1 h1 plus alpha2 h2 with minimal error. This construction can be repeated until iteration t, this number of iterations being a parameter of the boosting algorithm. The final predictor of the boosting thus has the form f0 plus the sum from t equal 1 to big T of alpha t ht. This predictor is therefore nothing more than a weighted sum of decision trees. Note that here the construction of the trees is sequential. Unlike random forest, the construction of each tree depends on the construction of all previous trees. It is therefore very difficult to parallelize this algorithm.